Okay, let's solve this first order linear DE using power series. Notice we could solve this using an integrating factor. It's just another way to solve it. So first off, our P of X here in front is 1. So we don't have any singular points. That never equals 0. So we can expand this or find the solution about any point. Will be easy and find the solution around x equals 0. So we assume a solution that has this power series. Take the derivative and we get this. Now we're going to plug that in here for y prime. Plug the original in here for y. Don't forget about the x hanging out there. We've got to bring this x in. We get an n plus 1 now. X to the n times x would be x to the n plus 1. Now I need my powers to line up. I need this starting point to be the same as this starting point, and this power to match this power. So first off, the first term here is 0 when it equals 0. So one thing I could do, and this will help a little bit, is this guy here, the first term was 0 anyways. I might as well start counting at 1. Sometimes that helps, sometimes it doesn't. We could have left that 0. Okay, now I want to get, so the trick here is these differ by 2. This guy is 2 bigger than this one. So I want my starting points to be 2 away as well. So one way to do that is break off the first one here, plug in n equals 1. To n equals 1, I get x to the 0, that's 1 times a1. So I broke off, really I've broken off the first 2 terms, just the first one was 0. And I made this guy start at 2. And the reason I wanted to do that was the difference between here and here was 2, so I want the difference between the starting points to be 2. Now we could play this game where I want these both to look the same. So they differ by 2. I'm going to go k equals n minus 2, which means n is k plus 2. Then if I replace everything in here with k's instead of n's, check these details on yourself, I would get this. Then look, they match up. It's index plus 1, index plus 1. Then the choice of index is completely arbitrary. It doesn't matter if I call it k, j, I. It doesn't matter what I use here. So I might as well use all the same. I could replace these and call them k's, or I could go backwards now and call these n's. Or the easier way to do this is the shortcut. I want this exponent to go up by 2. That means everything inside the sum needs to go up by 2. We counteract that by making this starting point go down by 2. Raise all these up by 2, raise this down by 2, or bring it down by 2. So that would get us here. Write this down, check those details on yourself. Write out a few of the terms here, starting at 0, and prove to yourself that you get the same thing you did with these terms starting at 2. Now that I've got the powers matched up, and the starting points matched up, I can squish this together into one single sum. So I've just kind of factored out the x to the n plus 1 and written this as one single sum. This can only be true. The only way an infinite sum, a power series, can equal 0 for every possible value of x is if every single coefficient is 0. Not the a1, we broke him off. All of these must be 0. Now, well, actually I lied. The only way all of this can equal 0 is if everything equals 0. So not only do all of these terms need to be 0, a1 must also be 0. So we say that a1 is 0 and what's inside here must be 0. We always want to solve this for the larger index, so n plus 2 is an over n plus 2. Just move that over and divide. This is our main goal, was finding our recursive formula. Once we get that, we're almost done. Okay, remember, the order tells you how many free parameters, how many free coefficients you'll have. We're first order, so A0 is going to be free. If this were fifth order, then A0 through A4 would all be free. Those would be our arbitrary constants of integration, like our C1, C2, and so forth. So A0 is free. A1 we said had to be 0 because this whole thing must equal 0. Now we start plugging into here all our different values for n. So start at n equals 0, that would be A2 is A0 over 2. Check these details on your own. Write down this formula, plug in n equals 1, n equals 2 into both sides, and so forth. N equals 2, we get this. N equals, this was important, A3 was A1 over 3, but A1 was 0. A5 is A3 over 5, but A3 was 0. So every other term is going to be 0. We're only going to get the even powers. Okay. So I've written out a few of the terms here. Check these details. Make sure you believe this. Here's my full solution. This keeps going on forever. I've only written out the first few terms. If you're curious, we could write this like this. And that is the power series expansion of e to the x squared over 2. So if we were to solve this using Laplace transforms or integrating factors, that's the solution we would get. You don't have to realize that. This is all we were after, writing out a few terms of this power series solution.